Hi, I'm Samir Sayegh. I am an ophthalmic surgeon and a physicist, and I'm presenting about UniversIOL, which is a universal computational tool to select the optimal intraocular lens for patients undergoing cataract surgery. We have a product that's being used by many people throughout the world, and I'm going to show specifically how Mathematica was a core technology that helped us get a very powerful and flexible tool. So come to the talk. Hi, thanks for coming to my talk. I'm Samir Sayegh. I'm an ophthalmic surgeon and I am also a physicist. And I'm going to talk, I spoke about similar things before, but I'm going to talk about the most common blinding disease in the world, which is cataracts, and how this can be reversed, and more specifically, how it can be reversed in a beautiful way, where you actually can see much better than you've ever seen in your whole life, hopefully. And then I'm going to discuss how we developed a computational tool that helps us do this, specifically selects an intraocular lens for a specific patient, for a specific eye, that will make the vision basically perfect. And of course, since we are here, I'm going to discuss how Mathematica has played a role in the development of this tool. Okay? So I will try to go pretty fast through the introductory part, and you can stop me anytime, and then hopefully we still can get dinner tonight. Okay? So credits, Stefan Leibrandt was a major contributor to the software development, and then a number of people from my clinic. And you may have heard about some of the other guys, such as this guy here. This is the abstract you've seen. So the plan of the talk, I'm going to talk about vision, blindness, and the universality of cataracts briefly. I'm going to show 3 models of reversing the cataract's blindness. And I'm going to show 3 things you really need to do to trend towards the perfect vision. And then I'm going to give 3 examples of how we use Mathematica to achieve that. So you may recognize this. This is a Picasso from the Blue Period. You can see it, I think it's in DC. This is the summary of your lives. So basically, you're born here, you die roughly here, and these are the eye conditions that you will develop, or people develop. They are fairly common. I have some percentages here. It does depend. If you live long enough, you will develop presbyopia. You don't need to be very old to have nearsightedness or farsightedness. If you live a little bit longer, you will definitely develop a cataract. And if you live a little bit longer, then you're definitely going to go blind from your cataract. So that's why 90%, anywhere between, say, 75 to 90% of the blindness in the world is due to cataract. So that's an important kind of little map. All right, and now nearsightedness is also a problem, and it's related to my talk. You'll see why a little bit later. But this shows you in a particular geography in Taiwan is placed, not only the fact that nearsightedness by the time you are 18 grows to the point of being nearly 80%, but through the years it has gotten worse and worse, right? So there are a lot of people who are, say, nearsighted, independent of having a cataract, because a cataract you get much later in your life. Astigmatism is a big problem. This is a very nice slide that I'm not going to discuss for the sake of time. But one point to understand is that astigmatism is really the worst of all. Because if you're nearsighted, you can see near. If you're farsighted and young, you can see far, right? If you have astigmatism, you cannot see anything. You cannot see near, you cannot see far. Everything is distorted, right? So getting rid of astigmatism is going to be very important, and if you can do it. And it's only very recently that we've been able to address this in a specific surgical way, in particular at the time of cataract surgery. So it's fairly recent development. Just to give you an example, I'm going to be talking sometimes in terms of diopters. The D here is for diopter. So if you have 1 diopter of myopia, this is how you see. 2, 3, you can see it goes blurry pretty quick. So if you miss your computation by 1 diopter, you're basically shifting your patient from seeing this crisp to seeing this. If you miss it by 3 diopter, then you're shifting your patient from seeing this crisp to that. So that's the importance of having really a good computation. Just for a historical reference, the first time the cataract surgery was done with an implant that was put in the eye, that's roughly 50 years ago, maybe 60 some. The error on the computation was of 20 diopters. Okay, just so that to give you a historical, perspective. We can do better than that, but it's not perfect, and we are in the game of making it much better, much closer, to what's on the left side. So here are some actual cataracts. I do operate cataracts of this severity, even in this country. So I'm operating this coming Monday. I'm going to be operating a bunch of them, maybe 20 or 25, but 2 or 3 would be this bad. Okay, generally speaking, in the Western world, they're not usually this bad. But once they are this bad, you really don't see anything. It's not going to be like this. I mean, if you have this cataract, you're not going to see that. You're not going to see anything. All right, so there are 3 real-world cataract environments, and I've worked in pretty much all 3, and I have collaborators and users of my system, my software, in all environments. One is a relatively early cataracts in the 2040 range. That's a vision 2040, so you're twice as bad as normal, with access to very high-tech tools. An example is the United States, Illinois, or San Diego. Okay. Then you have harder cataracts in the 2100 range, with good access to technology, maybe not as much as what we have here. Examples are Poland and Greece. Just these are specific places where I do have collaborators. And then the very hard cataracts, which is HM means hand motion. They can only see the hand move, or light perception, which is they can only see the light, right? They cannot see numbers, they cannot see letters, they cannot see your fingers, they cannot see your hand move. It's just if they have, is there a light or is there not? And this is from a cataract. And this is typically represented by eastern Mexico. There's certain places like the state of Oaxaca where I've operated, and I do have collaborators there. Okay, so what do you want to do? So what you really want to do, the first thing you want to do is to remove the cataract. And have we done this before? Yes, we've done it probably for hundreds, probably thousands of years. And there's been some techniques, not as elegant as what we have today, but people did this. And that was all they did. Now, if you just remove the cataracts, you have a lot of optical power in this lens, and if you remove it, it's gone. So now you're creating a very bad problem of farsightedness. And sometimes the patient can't see much more than they did before, right? So ideally, you want to correct that. So the second step is that you want to correct the myopia that existed or the hyperopia by implanting an intraocular lens, okay? The third thing you want to do is to correct the astigmatism. Okay? So the myopia and hyperopia, as I was telling you, it's about half a century that we've been able to do this, a little more. And to do it well, maybe a quarter of a century. Okay, so for half a century, we had something to implant to compensate for this power. And to do it well, maybe about a quarter of a century. Correcting astigmatism is more like an eighth of a century, maybe a dozen years or so, that we can have some device to correct for that. And then presbyopia is the inability to see near as you age. And that's in 1/8 of a century. We don't have anything that's good enough at this point. But we won't worry about this. We'll probably concentrate on the 3. So this is an intraocular lens. It's actually very, very small. This one in particular does correct for astigmatism. You can see there's dots here. So astigmatism has direction, right? So one direction is steeper, focuses light more than the perpendicular direction, all right? So when you correct, you can't just put a spherical lens because then you miss astigmatism. So you want to put a lens that itself has an asymmetry. And this asymmetry is marked by this little axis here. These are very, very modern lenses. We didn't have good lenses like this 50 years ago or 20 years ago. We're just starting to see them, as I said, in the past maybe 5 to 10 years, depending on how you want to count on the quality and whatnot. To calculate this, it does take a lot of work. And each manufacturer has their own little website and whatnot. This is a representation of astigmatism. This is steep, this is flat. You do a computation here, then you go to the company and they tell you, you enter the data and whatnot, and then they tell you which one to choose. The sites are very annoying. Each company has their own site, their own methods and whatnot. So here's an example. This is one company, other company, third company. So if I'm trying to find the optimal lens, it's like you're trying to buy a ticket, to fly to New York. So you go to American Airlines and you look and you find maybe a ticket and say, well, maybe United has. Go ahead.
A question on the robots. How do you adjust the eyesight on the robots for normal vision?
Okay, so most of what I'm going to talk about is for humans. Okay, and we'll talk about robots later, maybe at the end of the talk. Okay, thank you. So you're buying your ticket, you go to American, then you say, well, maybe United has something. So you go to United sites and you start looking for United. You say, okay, how about Southwest? And then you go to Southwest, and now you're doing the comparison yourself by hand, and there are, dozens of airlines, and then it's not very, very useful. And the companies are not going to be so nice as to provide you with others. So there are many others, and this is just a list of the companies that manufactures intraocular lenses. So what we wanted to do is to put everything together, right? To have a system that includes the spherical computations, meaning for what sphere do you need, okay? And for all intraocular lens manufacturers, so IOL means intraocular lens, with multiple formulas for optimization, to include correct toric computation, because there was a lot of confusion, even amongst the companies, on how to do the toric computation. Toric means the astigmatic part. People didn't know how to do it. And they were using algorithms that were inaccurate a number of times. These are some of the collaborators again. And I'm going to give some examples of what we did. So here's the basic architecture of our system. So we have a core calculator here that does all the computation for the intraocular lenses. We have a huge lens database. It's essentially universal. So I go everywhere. I talk to everybody. I have people in my clinic that connect to the different, every time there's a new lens, a new intraocular lens that appears, we know about it. We know its characteristics. We know its measurements. We know its power. We know everything about it, and we add it to our database. Okay, so that's a universal database. The calculator, there are different methodologies of calculating. So we have included, to the best of our knowledge, a lot of these if they are sound and accurate. And then we have a front end which is universal, which basically is a web interface. We have other ways of accessing that. So this is just an example of what you need to do. So you enter data about the surgeon and the patient and whatnot, and then measurement of the eye. What is the length of the eye? What is the curvature of the cornea? What is the desired outcome? Because the desired outcome is not necessarily always 0. It could be a little negative so that the patient can see a little bit more at near the computer and so on and so forth. So you enter a number of parameters, and then it gives you the best selection. I don't have a slide corresponding to this, but if you click on select lens here, it will give you a ranking of all of the lenses that you selected the brand and the models for, right? So you may say, oh, I love Johnson & Johnson. They're my best friends. I'm going to include them in the search. I love Alcon. I don't like Bausch & Lomb. I'm not going to include them, and so on. So you can pre-select, and this pre-selection is here. And then from the lenses that you selected, so you say, I don't like to fly United. I don't like to fly Southwest. They mess up they lose my luggage or whatever. So I don't include them. It's only the ones that you included that you would get there. So you have this, this kind of situation. All right. So now, okay, so it works extremely well. I can give you access, and we can see it run. But now, since I'm here, it's Mathematica time. I'll give 3 examples of how Mathematica was useful to develop this. Now, the summary is that we developed a lot of things in Mathematica, but the final implementation that's running on the server is written in C++. And the reason is because we were developing this when Wolfram was attempting with very variable levels of success to have a fully accessible, fully functional Wolfram language Mathematica implementation on the web. And but a lot of the core ideas are developed early in Mathematica and then fielded. So one of them is residual error computation. And basically what it is, so very broadly, all of these can be thought of the ability to solve inverse problems symbolically to allow solutions that would be impossible or impractical if performed only numerically. Okay, so if you were doing numerically, it would be prohibitive. But if you solve symbolically first and then run the solution numerically, then it works nice. So here's an example. If you want to know for a given intraocular lens that you put in, what would the residual error be? Okay, would it be -20, or would it be -3, or what? So there is a nonlinear equation that you need to solve. And if you solve it every time, you wouldn't be able to solve it for every single manufacturer, every single intraocular lens. It takes a lot of time. Here's an illustration, and this was shown by Stefan in a talk we gave together. So if you run it directly here, it's actually 1,000 runs, but you have a half a second. It takes half a second. If you solve it in Mathematica first, and then just run the solution, it does it in about 100ths of a second. All right? So you gain. So if you're going to try to be universal and calculate all of these lenses, okay, you have a tremendous advantage here, and you wouldn't be able to do it otherwise. Okay? Now, another example is astigmatism correction. And if you look here, this is astigmatism at the lens plane, and this is at the corneal plane. If you look at the ratio, this ratio is always 1.5. Okay? So this is incorrect. And this kind of belief has been maintained by many companies for a long time, maybe decades or more. So we did work that showed that, in fact, that ratio varies depending on, say, the power of the cornea and essentially the length of the eye. And it can be 1.5 for average eyes, but it can be as high as 2, and it can be as low as 1.2. And if you don't take this into account, you get lots of errors. So what we did with this is very simple math, but you can do it in Mathematica. There's a slightly more complex version of this, but I'm showing the simple version. So you basically extract what's called a toricity ratio, which is a ratio between the astigmatism value at the lens plane to the astigmatism value at the corneal plane. Okay? And then you can compute it, and in terms of things that you can measure in the calculator. So you can go into a specific calculator of Alcon, of Johnson & Johnson, of Bausch & Lomb, and see how they are doing it, if they're doing it correctly or not, simply by using this little formula here. And this was developed with Wolfram Gabra, who works for me. All right. I'll give you one last example and then open to questions and dinner. So the last example, again, this is the same IOL plane, corner plane. But what I'm trying to point here is that these toric IOLs, intraocular lenses, are discrete. All right? So at the corneal plane even, you go from 1 to 1.5 to 2 to 2.5, etc. Well, what if the patient has a value of the astigmatism that's in between? You won't be able to correct with that. Well, there's another technique, which is called relaxing incisions. Okay, you put relaxing little incisions in the cornea or outside the cornea, depending on what tool you're using, if it's a laser or a diamond knife or whatever. And you can get also correction. But the corrections are also discrete. So 1/2, 3/4, 1.5, 3. So if you have a patient who comes with 1.9 of astigmatism, okay, then one way or another, they'd be left with about 1/2 a diopter of astigmatism. And that's significant, right? It's not, they're not going to die, but it's not going to be perfect. And if other errors are also entering, they may end up with more than that. So how can you get this to 0? That's the question. So this is something I did in Mathematica. And basically the idea here is the solid circles represent what you can correct with incisions. And the dotted circle correspond to what you can correct with intraocular lens, or the other way around, it doesn't matter, right? And the intersection are points where if you combine them, then you can get perfection, 0 astigmatism. So nobody is doing this right now, but here's the example for the 1.9 patient. Actually, for several patients. For his 1.9 patients. So if you put your toric lens in this direction and you put your incision in this direction, then you will get 0 astigmatism correction. And here's a representation of the surgery itself. So that's the eye of the patient, that's the cornea. And what you would need to do, this is the axis of the steep where you have maximum curvature. This is your cataract incision, so you're going to be entering the eye from here, right? And so these are going to be the incision you're going to make with the laser or with the diamond knife, it doesn't matter. I mean, if you diamond knife, you'd put them a little bit behind. With the laser, you put them here. And then your actual intraocular lens, you would put in here. And then with combining these two, you get exactly 0. So you eliminate all of the astigmatism by this combination. Now, the methodology for this was developed a lot of the computations were done in Mathematica for the formal development. So anyway, so here's my conclusion. We have 3 main cataract environments, 2040, 2100, and hand motion. The biometric tools may be different, secondary to combination of the nature of the cataracts and the socioeconomics of the region. In most environments, you can still get excellent measurements and thus excellent results. The UniversIOL calculator is a powerful tool used in all environments with excellent outcomes. So all of these environments I discussed, we do have very, very nice outcomes, much improved compared to what they had before. Even in San Diego, which is a very fancy place, you know. The results are validated in these 3 environments. And then we have an extension of that, and I'm not going to talk about here. And Mathematica has been an effective tool at different junctures of developing this tool, this UniversIOL. And full online implementation in Mathematica is under consideration currently. So thank you very much. You can contact me, and I'll take a few questions now, and then we'll go to dinner. Thank you.